Hola a todos, ¿qué tal? Bienvenidos de nuevo al seminario de álgebra. El día de hoy tenemos el honor de tener un invitado, a Feyisayo Olukoya, quien nos va a hablar sobre the mapping class group of a shift and the Higman-Thompson group. Thank you very much, Shayo. We are very glad to have you here, that you talk to us here, and we're looking forward for you to hear your talk.
Yeah, thanks very much for the introduction, Alonso, and thank you also for the invitation. I'm delighted to be giving this talk to the seminar there. I don't know what the traditions are where you are, but I mean, I guess if you have questions, then feel free to interrupt. I wouldn't be able to kind of keep an eye on what's happening in the chat, so hopefully someone will kind of inform me if there's a question.
Sure.
And I've just
I'll let you know in case there's any question.
Yeah. All right, thank you very much, Alonso. Right, so I will be speaking about the mapping class group of a shift of finite type and the Higman-Thompson group. And I should say that some of this work is supported by EPSRC grant and the Lever-Hume research grant as well. Okay, so just an overview. I'm going to begin just by kind of motivating the topic. And then I'll go on to introduce some of the key actors. So looking at the automorphism group of a shift of finite type and how these can be described using sliding block codes. And then we'll go on to introduce the mapping class group, as well as a related, what are called flow codes for constructing elements of the mapping class group of a shift of finite type. And then I'll introduce the automorphism group of the Higman-Thompson group, and then briefly kind of talk about how the two are connected. In particular, the takeaway is that the mapping class group of the full shift, two-sided shift over n letters, is isomorphic to the automorphism group of the Higman-Thompson group, Gn n-1. There are some collaborations that I should mention. Some of this work, some aspects have been kind of developed together with Jim Belk, who is at Glasgow, with Colin, my PhD supervisor, who is at St. Andrews, Peter Cameron, whom I just discovered has retired from St. Andrews. There is a computational package that we developed for computing in all of these groups. There's an early version of it released on GAP. This is the AAA package and has been developed together with Colin and some of his PhD students, so I guess my siblings, so Luna Elliott and Fernando Flores Brito. Right. Okay, so the motivational, where's this work coming from? I think at least for me, the start of the story is in our characterization with some of the collaborators I mentioned of the automorphism group of the Higman-Thompson group using transducers. And coming out of this characterization, we immediately observed that there was a subgroup whose elements kind of naturally induced automorphisms of the two-sided shift space. And in particular, we've kind of understood the extension that kind of connects the subgroup of the automorphism group and the automorphism group of the two-sided shift. In particular, we also understand the two cocycles associated with the extension. And then, well, the question is, can we extend this to the bigger group, so the automorphism group of the Higman-Thompson group? And we immediately run into an issue, which is that, and we'll kind of elaborate on this problem a little bit down the line. There was an immediate obstacle in the action of the bigger group, in that you can do what's called kind of stretching and compressing time. And we didn't immediately see how to connect the two things together. But I was at a recent Thompson group conference, and I met someone from the shift community, and they pointed out that, well, the mapping class group might be a natural thing to look at. And so that's what I'm going to talk about today. So how the mapping class group of the full two-sided shift relates to the automorphism group of the Higman-Thompson group. There, I should mention other connections between shift spaces and Thompson group, and these are coming out of the body of work being developed by Matsui, Matsumoto, Nekrashevich, amongst others. So looking at full groups of topological groupoids associated with certain shift spaces. Right. Okay, so I'm going to now introduce in a little bit more detail the two-sided shift and how you can describe elements using what are called sliding block codes. Okay, so for the purposes of what follows in this, well, and actually in the middle of the talk, we're going to restrict to full shifts. What I present in this particular section of the talk, so about the full shift, will also apply to shifts of finite type and various other generalizations. Okay, so what do I talk about when I talk about two-sided shift? And this is maybe a little bit technical, but here we go. We're going to fix an alphabet of size n, and normally we'll denote the elements using the symbols 0 to n minus 1. And you can consider the Cantor space of bi-infinite sequences. So I'm taking the discrete topology and then the product topology. You get a Cantor space out of this, this bi-infinite sequence space over the alphabet. And there's the shift map, a homomorphism of the space, which you can imagine just kind of, pulls the sequence to the left, right? And here's a formal definition that's on the slide. And the pair consistent of the shift map and the bi-infinite sequence space, x into the z, this is the two-sided shift dynamical system. An automorphism of the shift dynamical system is just a homomorphism of the bi-infinite sequence space that commutes with the shift map. So applying the shift and then the homomorphism, you get the same result as first applying the homomorphism and then doing the shift map. Right, okay. Hopefully those definitions were fine. There's a classic result. Well, it appears in a paper of Hedlund, but then there are other people associated with the result as well, so Colchester and Linden as well. And this is that an automorphism of the shift can be given by a sliding block code. And I'm just going to elaborate a little bit on what sliding block codes are. I'll put up the definition and then try to give some intuition about what it's saying. So imagine that you fix a window of size 2r plus 1, and you fix a map, right? So from the alphabet to the 2r plus 1, so words of length 2r plus 1 to xn. And the way sliding block code is defined is I run my window along my bi-infinite sequence, and depending on what I see in that window of length 2r plus 1, the map F tells me where to send the midpoint of the window, so the point x high here, where I map, where I map that point to. This gives me a shift commuting, and if you want an exercise and if you get bored with what I'm saying and you like something to keep your mind occupied, then it's an easy, it's a straightforward exercise to verify that the resulting map is a shift commuting and continuous map on xn to the z. Such a map is called a sliding block code. Okay, so here's an example just to kind of illustrate what this looks like. So here's my map, and I define it in a piecewise fashion. So depending on what the final letter is, the kind of last two letters are in a window of length 3. So I'll just give you a second just to kind of take in the definition of the map. Right, so, let's see what it does to a sequence. So I've just kind of generated a sequence here, and we're going to apply this map to see what we get out of this sliding block code. Right, so I'm starting from plus infinity. We just carrying on at zeros all the way to plus infinity, and so the window of length 3 around this point, it's just 3 zeros, and so that tells me that this central point here should map to 0. And then I move my window along, and that tells me where the next few points go to. And then you can carry on in this way. So I guess here's a more interesting one. So we're looking at the point 1 here, so this is 2, 1, 0. We ended in 0. The next digit is 0, 1, so that tells me that I output a 0. And then you carry on. Again, we have a 1, 2. So we ended in a 1. Next digit is a 2, so I write a 0, and so on, and so on, and so on. And hopefully you can see that this is the sequence that you get out of this sliding block code. Right. An interesting fact is that the square of this automorphism is the shift squared. And again, if you like something else to keep you occupied, this is another thing that you might try to verify. Just applying the definitions of the shift of 3 letters and the definition of the map f infinity here. Okay, so here's the kind of famous result due to Curtis, Head, and Linden, which is that every automorphism, and in fact endomorphism of the shift dynamical system, can be described in the way that I described that map on the previous slide, so using a sliding block code. There's another connection to, I guess, for any theoretical computer scientists in the audience, you might recognize sliding block codes as one-dimensional cellular automata, and this has been a rich way of approaching automorphisms of the shift. So here's a sketch of the proof. Suppose I have an automorphism of the shift. I consider the cones where I specify, the at index 0, the letter is I, and then you can have whatever you want, right? At other indices. And VI are the preimage of the UI. The VIs are clopin and disjoint, and in particular, I can give them as a union of basic open sets of length, say, 2r plus 1. And these sets tell me how to define what my window does to the index at the center of the window. In particular, I define a map from words of length m to xn by mapping it to I if it lies inside, if the corresponding cone lies inside VI. And you can check that that this sliding block code gives rise precisely to the automorphism phi that we started off with. Right, so that's the Curtis, Hedman, Linden result. And there have been many kind of methods for coming up with or creating elements of automorphisms of the shift. One important and rich vein for coming up with elements are so-called marker constructions. And this is kind of similar to sliding block codes. What you want to do is you want to fix markers, so kind of non-overlapping words, and you specify what happens between the markers. So whenever you see a word between markers, you kind of know what to do. And the non-overlapping condition means that you get a well-defined shift commuting endomorphism of the shift. And then using the marker construction, there have been numerous embedding results, and these are coming out of works of Feyisayo, Boyle, Franks and Kitchens, and amongst others. So one can use the marker construction to show that the automorphism groups are bi-embeddable. I should also mention Keim and Rausch, right? They use the variance of the marker technology to prove really important results. And the automorphism group of shift contains free group on a countable number of generators, countable direct sum of finite groups, and you can also use the marker construction to prove undecidability results. In particular, again, this is kind of linking into the people coming at it from the theoretical computer science side, where they're kind of viewing these as cellular automata. Right, and yeah, you can show that the other problem is undecidable, the conjugacy problem is undecidable, and so on. Right. And then another kind of important tool for studying automorphisms of the shift are the actions on periodic points. And yeah, periodic points when you mod out by the shift, and you can use this action to show that the automorphism groups are residually finite, right? In particular, the groups act faithfully on the periodic points, and then you can kind of separate them out as you kind of increase the period. You can use this also to show that they are not finitely generated, and a result used for Ryan, which is that the center of the group is the group generated by the shift map itself. Okay, and this is, I think, mainly work of Boyle, Krieger, and possibly Bowen-Franks and Kitchens as well. Okay, and yeah, you can use these also to construct conjugacy invariants. So this is, as far as I know, some of the key tools for kind of understanding automorphisms of the shift, macro construction, and the action and periodic points. Another important thing that I should mention is what's called the dimension representation. And without kind of getting into too much detail, you can define it in a number of different ways. And there's a kind of dynamical definition. And what it is a homomorphism from the automorphism to the shift to the automorphism group of the integers that join 1 over n. And the kernel of this homomorphism has proven to be of significant interest, or understanding the kernel, I think is one of the kind of is a kind of a key, will be a key to kind of understanding the automorphism groups better. Okay. Right, so that's kind of one of the main characters introduced. I'm going to go into the second main character, which is the mapping class group of a shift of finite type. And in order to do this, I need to introduce the notion of flow equivalence. And just as an overview, the flow equivalence fits into an algebraic framework for classifying shifts, a shift of finite type. There are kind of other forms of equivalence of shift spaces. There's a strong shift equivalence and shift equivalence, and strong shift equivalence corresponds to topological conjugacy. Shift equivalence corresponds to what's known as eventual topological conjugacy. Right, and all this kind of classifications are known. And the classification up to flow equivalence is due to Franks, who's building upon work of Parry and Sullivan. Oh, and here's the takeaway, I guess, for understanding how flow equivalence kind of relates to shift spaces. Well, it's to the automorphism group. So the mapping class group is the flow equivalence, what the automorphism group is to topological conjugacy. So in particular, flow equivalence shift spaces have isomorphic mapping class groups. All right. Okay, so we're going to kind of get into some definitions, which will enable us to kind of say precisely what it means for two shift spaces to be flow equivalence. And from that, we'll build the definition of the mapping class group associated to a shift of finite type. So what is a flow? Right, and I should mention that in the section that follows, this is based on a paper of Boyle, Eilers, and Carlsen. And if you would like kind of more detailed exposition of this, then I highly recommend that particular paper to you. So Y is a compact metric space, and the flow is just a fixed point free action of the real numbers on Y. And what does it mean for two space flow pairs? So we call the space Y and the flow on the space flow pair. What does it mean for such pairs to be flow equivalent? Well, firstly, I need to introduce what a flow map is. This is just a continuous map between the spaces that restricts to an rotation preserving homeomorphism on flow orbits. So it maps flow orbits to flow orbits in a non-rotation preserving way. And yeah, it's a local homeomorphism. And a flow equivalence, well, in a special case when the flow map is a homomorphism between the two spaces y1 and y2, then that's what's called a flow equivalence. We're also going to need the notion of isotopy to kind of state the definition of the mapping class group. If we have two flow equivalences between space flow pairs, then they're called isotopic if, well, I can find a continuous map from the first space direct product with the interval to the second, such that, I continuously deform from the first equivalence to the second, and right, all the maps in between are also flow equivalences between the two, the corresponding spaces. A little bit kind of later on in our talk, we'll see some examples of this. So if this definition is a bit mysterious right now, then I urge you to stick with me. We shall see some examples in a few minutes. Okay, so how does this relate to the shift? Well, the first thing that you do is you do construct what's called the mapping torus of the shift. And here's the definition, but perhaps a more intuitive definition is that I look at the quotient of the shift across the reals, modulo the z-action, which is generated as on the slide, right? So I kind of identify points in the same orbit, right? And you take the quotient, and that gives you the mapping torus. And this, it turns out, is a one-dimensional compact matrix space, and kind of straightforward to verify. Verify this is true. Again, if you like another exercise to keep you entertained, then this is something that you might like to try. And just to kind of give you some intuition about what's going on, so periodic points, so these are points with finite orbits under the action of the shift. Well, this corresponds to circles in the mapping torus. Non-periodic points are just lines in the mapping torus. And then using this mapping torus, we can define a flow, what's called the suspension flow on it. And with this, we'll kind of define what it means for two shift spaces to be flow equivalent, right? Right. So what's the suspension flow? Well, it's kind of the natural action of R on the mapping torus. You just act in the natural way. This gives you what's called the suspension flow, and we see that two shift spaces are flow equivalent if the suspension flows and the mapping tori are flow equivalent. All right, we are kind of, I guess, over halfway through. Any questions at this stage? People just, it's very, I mean, this reminds me of the pandemic, speaking to a screen and I can't see it. I can't see the people I'm talking to.
Just one quick question there. Right. Okay, no, so sorry, because I saw at some point you had defined the shift space, but over the naturals, but you consider it over the integers, right?
Right. Yeah. So over the integers, so it's by infinite sequence space. So I think that was probably a typo.
Okay. No, maybe I was just, I think I didn't see correctly. Okay.
Right. Yeah. No. So yeah, we're looking at the full two-sided shift.
Okay. Thank you.
In this section. Yeah. Actually, throughout. Yeah. Thanks for the question. Right. Yeah. So that's what it means for two shift spaces to be flow equivalent. It means that the suspension flows and the mapping tori are flow equivalent. And then, well, how do we? How's the mapping class group defined? Well, first of all, we take the group of all flow equivalences from on the mapping torus of a particular shift space, and then we quotient out by the subgroup consistent of all the elements that are isotopic to the identity. And just as an aside, this group is simple, and actually there've been some interesting connections related to these groups. This is by Boyle and Chuysurichay, where they construct left-orderable Thompson-esque groups from I think as subgroups of the of the group of flow equivalences isotopic to the identity. Anyway, yeah. So the mapping class group, you take the quotient of the group of flow equivalences by the subgroup of elements which are isotopic to the identity. This is similar to the way mapping class groups are defined for surfaces, but I mean, it's a very kind of different context, and they're, I think the similarity is probably kind of superficial. I mean, goes maybe as far as the definition, but yeah, maybe that's kind of too strong to say. But it'll be interesting to see what kind of analogies actually one can pass through from the mapping class group for surfaces to this particular context. But I must confess, it's not my area of expertise. Right. So similarly to how you can describe automorphisms of the shift using sliding block codes, Boyle, Carlsen, Eilers, and others shown that you can do a similar thing for flow equivalences. And at the heart of it is what's called a discrete cross-section. What that is, well, I take a closed subset of the bi-infinite sequence space such that any point in the full two-sided shift space is in the forward orbit of some point in the closed set C. And secondly, I have a continuous return time map, right? So in particular, this is a map from the closed set to the naturals, and just kind of tracks when a point under the action of the shift gets back into the set C. Right. So in particular, this tells me that a consequence of this is that the set C is open. Right. As a closed set with these two satisfying these two properties will then be called a discrete cross section for the shift map. Associated to a discrete cross section is the continuous return map, which is, well, the map that's right. The point X returns to C at after Rx applications of the shift map. Where does it actually get to? And that's what the map rho C tells me. Okay, so how can I use discrete cross sections to help us understand flow equivalences? And here's the construction of flow codes. And so here's the idea. I have two discrete cross sections, and additionally, I have a morphism of return maps. So this is just a map from the closed set C to the closed set C prime that kind of intertwines or commutes with the map rho. So in particular, doing psi first and then doing rho bar is the same thing as doing rho and then doing psi. I hope I said that the right way around. Right, if I have such a morphism of return maps, then I can use this to construct a flow map in the following way, right? And what you want to do is, right, so this point X returns to C at a certain time, and I'm just going to stretch, right? I'm just going to kind of stretch out time such that when X gets back to C, then its image on the psi will also return back to C prime. And here's the kind of natural formula. If you want to if that's what you want to do, then this is a formula that you write down to achieve that that goal. Right, and here's the result. Up to isotopy, flow equivalences are induced by morphism of return maps. And again, in a second, we're going to kind of tease this a little bit further to see how we can associate what are called flow codes to flow equivalences. Right. Okay, so how do we kind of construct the flow codes? Again, we're going to fix a discrete cross-section. We have the return time map and the continuous return map. And what we're going to do is we're going to kind of, if I take a sequence in C, I'm going to kind of divide it up according to when I get back to C, right? And this is what's called the return time bisequence. So using the return time bisequence, I'm essentially going to kind of divide up this bi-infinite sequences, this bi-infinite sequence X, into blocks of length. Well, when do I next get back to C? Right, and that's what we've done here. And then you can think about these blocks as letters in some alphabet with a kind of natural quotient map from your original, from your space C to this kind of new shift space with this new alphabet. And a morphism just kind of induces a shift commuting map on these new spaces. And in particular, a consequence of the Cortes-Leydon-Hedlund result is that, well, now these can be given by sliding block codes. And so I can understand a morphism. I can understand a morphism of this discrete cross-sections as this sliding block codes, right? So the sliding block codes arising from this, from the new spaces that I can associate with the discrete cross-section, entirely recover the morphism between the discrete cross-sections C and C prime. Right, and this is what's called a flow code. So just to kind of tie it back in with the idea of the sliding block codes that we saw before, what we do is we kind of partition the elements of C according to, well, when do I next get back to C? And then I can specify a map on this new alphabet, so the alphabet corresponding to the blocks, to the words, in the blocks, right? I specify a window and I specify, well, how do I transform the thin in the center? And that kind of gives me right, that gives me a well-defined map that kind of recovers the morphism that we started off with. Okay, so let's see some simple examples, right? So here are the examples I promised a while ago. Right, every automorphism of the shift induces a flow equivalence, which is a flow code. In particular, the sliding block code actually gives you the flow code. If you have a flow equivalence which preserves the length of circles, remember circles correspond to periodic words in the mapping tori, right? So if you have a flow equivalence that preserves the length of circles, then actually this is a flow equivalence that's coming from an automorphism of the shift. So again, the sliding block code that gives you that automorphism gives you something that's is isotopic to this flow, to the original flow equivalence. The shift map itself is isotopic to the identity, and you kind of do this in the natural way. So I'm just going to gradually slide along. So starting off with the identity, and when S is equal to 1, then this is x1, which actually corresponds to sigma, the shift map on x, 0. Right. Any flow equivalence which preserves circles is isotopic to the identity. So if you not only kind of preserve the length, but actually map a circle to itself, right, then actually a consequence of Ryan's theorem, right? Such a map has to be induced by an automorphism of the shift, and by Ryan's theorem, it must lie in the center, and therefore it must be isotopic to the identity. Okay, I'm going to give some properties of the mapping class group, and this arise in a subsequent, or maybe contemporaneous article of Boyle and his PhD student Chuysurichay. Well, it's countable, first of all, and this, I don't know, I mean, maybe you can say this from the definition, but yeah, I guess you can see it from the fact that it comes from, you can describe such maps using flow codes. It has a non-trivial automorphism group, which is essentially coming from kind of reversing direction or kind of swapping past and future. For, if that makes sense to you, then that's where this non-trivial automorphism element is coming from. It's not residually finite, and they show that it contains the infinite symmetric group. So yeah, it also has a trivial center, and this is really just coming from the action on periodic words extending Ryan's result. It acts faithfully and m-transitively on circles for every m. Right, and then you have the analog of the dimension representation, and in this case, it's what's called a Bowen-Franks representation onto the units of Zn minus 1. Right, when I kind of finished reading this article, I immediately recognized that actually all of these properties are properties that the automorphism groups of the Higman-Thompson group have. And I was, it was clear to me that since going based on the evidence that, you have this subgroup Ln of the automorphism group of the Higman-Thompson group that induces automorphisms of the shift, then it seemed clear to me that the full automorphism group should be isomorphic to the mapping class group. And it turns out that that's the case, and that's what this third part of this talk is going to be about. And I'm going to introduce the main actor in this section, which are the Higman-Thompson group and the outer automorphism group. And to close, then I'll briefly sketch out how you might go about showing that the mapping class group is out Gn n-1. I have written the paper. It's in a very rough state, and I'm hopeful that I will put it up at some point on the archive for other people to have a look at as well. Okay, so I'm going to begin by introducing the rational group. And first of all, with rational maps, we're going to fix a compact subset of counter space and a conjugate injective map from this set into the counter space. And if I fix a basic open set of cone, then the local action on that set is, well, I act on the set with my continuous injection, and then I strip away what I'm guaranteed to write. Okay, and this will give me a new continuous injective map, and it has this interesting property, which is that if I look at the local action of the map H at the word UV, then it's actually equal to the local action of the map H, of the local action of H at U at the point V, on the cone corresponding to V, corresponding to the word V. Whenever such a map has a finite set of local actions, then it's what's called rational, and we're going to use this log H here to denote the local actions of such a map. Right. I mean, if for anyone who's kind of familiar with the rational group of Grigorchev, Nekrashevich, and Shchensky, well, this is precisely the rational homomorphism of the counter space Xn at the end. Right. Okay. So, I mean, if you're familiar with transducers, then perhaps those last two conditions on the slide would have given you a clue that maybe there's some finite state machines lurking around, and indeed they are transducers lurking around. If I have a rational map, then I can get from it a corresponding transducer which induces the map. And I'll just kind of, with this example, kind of say what I mean by a transducer inducing a continuous map of the Cantor space. Well, first of all, you need to fix a starting point, and in this case, we're going to start at the state A. We're given some inputs, which is a one-way infinite word over the alphabet. I'm going to read these inputs starting from the point A, and then kind of keep track of what I write as I go along. And the image of my input point, well, it's exactly what I wrote out as I walked this finite state machine within the input word. In particular, you can check that this state A is going to induce a homeomorphism of the ternary Cantor space. And yeah, the state B will also induce a homeomorphism, whereas the state C is just going to be a continuous injection from the space into itself. As I said, any rational map can be represented by a transducer, and if you choose your transducer correctly, then the local actions of the rational map are exactly the states of this transducer. And well, what do you go to when you read a word from a state? You go to the local action at that word from that state, right? Okay, so those properties that I defined on the previous slide kind of tell you how to transition. And what you write, well, you kind of write the guaranteed outputs when you acted by the local action on the basic open set corresponding to the word. Right. The other kind of important property is it's what's called synchronizing, and which is that for any k and if I fix a word, there's a case such that if I fix a word of length k and I look at the local action of a word of length k from any states, then I have a guaranteed destination. I know exactly what the new local action is going to be. And just to illustrate that, so translating this into transducers, you can see that if I read a word that ends with a 1, then there's only one place I'm going to end up. I'm going to end up at the state A, right? And if I read a word that ends in a 2, then I know exactly where I'm going to be. I'm going to be in the state B, and so on and so forth. Okay, and that's the synchronizing property. And this property allows us to define what's called the core of a synchronizing rational map. And these just are exactly the local actions corresponding to long enough words, so words that are kind of longer than the synchronizing length. Okay, so for example, if we look at this rational map here on the slide, well, actually, its core consists exactly of the 3 states, A, B, and C. Right, so how does all of this, well, actually, how does all of this relate to the Higman-Thompson group? Well, a way of defining the Higman-Thompson group are as rational homeomorphism of a closed subset of Cantor space. And in particular, they have 2 additional properties. So they're rational, they're synchronizing, and they have a core that's just the identity map, which is that whenever it reads a symbol, then it's just going to write that symbol out. And here's an example. So the core of this example is the identity map. And all right, you can see that it's synchronizing because, well, if I read a long enough input, I'm just going to end up at the state ID here. And for those who are interested, you can try to verify that this, I think, is one of the standard generators for Thompson group F. So if you've kind of run out of energy, then here's another interesting exercise to rejuvenate yourself. Right. Yeah. So the Higman-Thompson groups are generalizations by Thompson of a tree of finite simple slash almost simple groups that were created by Thompson, and in particular, they are simple when n is even. Otherwise, the derived subgroup is simple. Okay. Right. So we can define an equivalence relation on rational maps by saying that two are equal if they have the same set of local actions. And then I can form a monoid whose elements are synchronized in rational maps, which are core. So, well, they're equal to their core. And the theorem that enables us to kind of characterize the automorphism group of the Higman-Thompson group is the one that's on the slide, and namely, they are the largest inverse closed subset of this particular monoid. Right, and here are some properties that we developed I developed together with some of the collaborators that were on the slide at the start. Well, it's countable. It has a non-trivial automorphism group. It has a trivial center. It acts faithfully and M-transitively on periodic points. And there's homomorphism, which we call the signature map to the group of units. And in particular, this homomorphism helps us to kind of characterize how the automorphism groups of the GNR sits inside Gn n minus 1. In particular, the automorphism group of GNR are the elements whose image under the signature map stabilize the point R under the action of the units mod n minus 1. In particular, the group ON1 is the kernel of the signature map. It contains an isomorphic copy of the automorphism group of the full shift on over any alphabet. And you might recall that, well, actually, this list of properties is almost exactly the same as the list of properties that I stated for the mapping class group. And that's because the groups are isomorphic. And in this kind of last 2 or 3 minutes, I'm just going to briefly give an indication of how how one might go about showing this result. The document is written. At some point, I would have cleaned it up enough to my satisfaction to kind of put it up on the archive. The forward direction just kind of makes use of the fact that flow equivalences are given by flow codes. And in particular, I can use the fact that these flow equivalences are given by flow codes and particular morphisms of discrete cross-section to understand that this morphism must actually be given by synchronizing rational map. And then it reduces to a question of showing that two isotopic flow equivalences give rise to the same rational map. And then the last stage is to then realize actually that the rational maps I'm getting out from this flow equivalences have cores which are elements of ON. And in the article where we kind of and subsequent ones where we kind of understand the automorphism groups of GNN minus 1, there are certain conditions that such a map has to satisfy if it's going to be an element of ON, and then it just reduces to checking that those conditions are satisfied for the rational maps corresponding to flow equivalences. Right, and then you realize that this is an embedding, using the fact that in both cases you have a faithful action on periodic points, and in particular, when you pass from this flow equivalence to this synchronizing rational map, you actually preserve modulo the action of the shift. You preserve the action on periodic points. And the reverse case, well, I'm going to illustrate this with an example. And the challenge for the reverse case is, well, given an element of out GNN minus 1 of out GNR, you can represent it by a transducer, and then you somehow want to kind of find, you want to find discrete cross sections for the shift that are kind of arising from this corresponding to this element of out GNN minus 1. And in particular, you can do so using the transducer you use to represent the element. In particular, given such a map, you construct what I termed a write time sequence, right? Which is right the next point at which I'm guaranteed to have written something, right? So you partition your sequence according to, well, when have I next, as I read this bi-infinite sequence through the transducer, when do I next write something? And the resulting closed subset of the shift space is actually a discrete cross-section, and is a way to associate a corresponding cross-section to this discrete cross-section. And I have an example on the slide here for this particular example. Right, and then you show that the map from the two cross sections is a morphism, and you use that to induce a flow equivalence, and that's how you kind of go in the reverse direction. Okay, so my example carries on, but I think that's all I wanted to say on this topic. Here are some questions that we would greatly love to know the answer to, which is whether or not the kernel of the dimension representation now, which we now understand to be the automorphism group of GN1, well, is it simple? Is it finitely generated and an ambitious one? Whether or not it's perfect, right. If there are more automorphisms of out GNN minus 1, beyond that, that's just kind of coming from swapping the past and the future. All right, that's everything I want to say. Thank you very much again for the invitation, and yeah, please fire away with any questions you might.
Thank you very much. Okay, so are there any questions? Well, let me ask you something, because I don't know, maybe you are aware, but people working with cellular automata and even with symbolic dynamics, we are sometimes interested in replacing so you work with a group of integers, right? And you get this. But sometimes we have been interested in replacing this group of integer by another group. Sometimes we want the group to be, for example, amenable or residually finite or other things.
Yes.
Do you think that there's like hope? Because it seems, I think maybe one of the most difficult parts is to generalize this machinery of the transducers. Like when you work with another group that is not just by infinite sequences.
Yes. Yeah, no, that's a very good question. And right, so the ex-student of Collins, Luna Elliott, whom I believe is now in Manchester, at least last I checked, she is currently based in Manchester. So they have an article that kind of extends some of these ideas to the so the Bowen-Thompson groups, right? So the DVNs, right? And in doing so, they kind of develop an extension of transducers where your inputs could be monoids.
Okay.
Right. So then I think this would be a natural framework, right, for looking at where you kind of move away from the integers to other types of groups. So yeah, I recommend that article to you. This is Luna. Well, I mean, then they were called Luke Elliott. I think that article is under their previous name of Luke Elliott, and it's understanding the automorphism group of the Bowen-Thompson group.
Okay, great. Thank you. I'll have a look.
Yes.
Okay. Any other question? Okay. Well, thank you very much, Shayo, for giving the talk, and thank you everyone for being here. Here you have the So you see that it's not just an empty room.
All right, yeah. Well, thank you all for thank you all for attending, and thank you again for the invitation. It was my pleasure to speak.
Thank you very much. Thank you.
Yeah.
See you. Bye.
Yes. Yeah. Cheers. Bye.